Good morning, class. Let us continue with our previous section. So, we are going to the module 1, chapter 1, section 1.1, the continuation. So, in the continuation of this session, we are going to introduce a new definition. We are familiar with the word linearly independent subset or linearly independent set. Now we are extending it to a different level. The vectors x1, x2, etc., xn are said to be linearly independent relative to the subspace E1 of the linear space E if whenever summation I equal to 1 to n ai xi is an element of E1, then it follows that a1 equal to a2 equal to etc. an must be equal to 0. So there is a slight difference from our usual concept or usual definition of linearly independent set. So the difference is that summation I equal to 1 to n ai xi, whenever it is an element of E1, the corresponding scalars must be equal to 0. Now, next what we have is, we have a lemma. So, the lemma is about, it gives us an idea about the dimension of the quotient space. Now, I'll give you a brief description about the lemma. It is lemma 1.1.4. So the basic idea of this lemma is that dimension of the space, quotient space E by E1, where E is the linear space and E1 is the corresponding subspace, is n if and only if we can find vectors, say x1, x2, etc., xn are linearly independent vectors of E1 such that there exists a unique y element of E1 such that for every x belongs to E, we can write x as summation ai xi plus y. For every x belongs to, we can write it as summation I equal to 1 to n ai xi plus y. Also, this lemma also states that the coset x1, x2, etc., xn forms a basis of our quotient space E by E1. So this is the basic idea behind the lemma. Now let's come to the proof of this lemma. First, let us suppose that x1, coset x1, coset x2, etc., coset xn forms the basis. Is the basis of the quotient space. Now we need to prove that x1, x2, etc., the vectors x1, x2, etc., xn are linearly independent related to E1, and also the equality, that is x is equal to summation I equal to 1 to n ai xi plus y. So for the proof, suppose coset x1, x2, etc., xn, coset xn is a basis of E by E1, the quotient space. We can write that summation ai coset xi equal to 0 implies each ai is equal to 0, because this set forms a linearly independent set for every I. Now using this, we are going to show that the set x1, x2, etc., xn are linearly independent. Now suppose summation ai xi equal to 0. Okay, this implies coset summation ai xi will be equal to coset 0. Now by the property of coset we have summation ai into coset xi equal to coset 0. Now this further implies that each ai must be 0. Why? Because the set coset x1, coset x2, coset etc. coset xn is a basis, so they will form a linearly independent set. So whenever summation ai coset xi is 0, we can conclude that each ai must be 0. Thus we have proved that x1, x2 etc. xn is linearly independent relative to the subspace E1. Now next what must we show? We must show that we have to prove that x will be of the form summation ai xi plus y, where y belongs to E1. So any coset say x can be written as the linear combination, of the vectors x coset x1, coset x2 etc. coset xn, because it is a basis. So we have coset x is equal to summation ai xi, summation ai coset xi. Now this can be written as summation ai xi. This is by the property of definition of cosets. Now this can be further written as, from this, that is coset x is equal to coset summation ai xi. From this we can obtain x can be written as summation ai xi plus some y, where y belongs to E1. This is simply by the definition of coset. So we have proved what was necessary. Next, we need to show the uniqueness of this definition. So suppose that x is equal to summation bi xi plus z, where z is an element of E1. Then since we have already defined x before earlier, we have summation ai xi plus y is equal to summation bi xi plus z. Now rearranging, we obtain summation ai minus bi xi is equal to z minus y. Now this z minus y is an element of E1 because E1 is a subspace. Therefore, we can conclude that coset summation ai minus bi xi will be equal to the coset 0. This is by the definition of the coset. Now this implies summation ai minus bi coset xi is equal to coset 0. Now since coset x1, coset x2, etc. coset xn is linearly independent, we obtain ai minus bi is equal to 0. And from this we can conclude that z minus y equal to 0, or in other words z is equal to y. So ai and bi's are equal, z is equal to y, so we can conclude that x has a unique way of representation. Now coming to the converse part, we are assuming that for every x belongs to the space E, we have x1, x2, etc., xn linearly independent vectors such that x is equal to summation ai xi plus y, y is an element of E1. This is our assumption now, and what is there to prove? We need to show that the dimension of E by E1, quotient space E by E1, is n, and or in other words coset x1, coset x2, etc., coset xn forms a basis, of E by E1. Now let us go to the proof. So to show that set is a basis, we need to show that it is linearly independent and spans the given space. So first, suppose summation ai coset xi is equal to the coset 0, and by definition we have coset summation ai xi will be equal to 0, and from this we can conclude that summation ai xi equal to 0, and since x1, x2, etc., xn are linearly independent, we can conclude that ai is equal to 0 for every I. So whenever summation ai coset xi was 0, we obtained that ai is equal to 0, so they are linearly independent. Next we need to show that the set coset x1, coset x2, etc., coset xn spans E by E1. So for that we have x is equal to summation ai xi plus y. Now this implies x minus summation ai xi is equal to y, which is an element of E1, and therefore coset x minus summation ai xi will be coset 0, which implies x minus summation ai xi will be 0. Therefore x can be written as the linear combination of each xi, and in the end, using this equality we have obtained that x is equal to summation ai xi. Now this implies coset x is equal to coset summation ai xi, and this is equal to summation ai into coset xi. So for any coset, say coset x, we have obtained it as a linear combination of coset x1, x2, etc., coset xn. So this is how we can prove that lemma. Now coming back to our section, what we have is we are going to introduce the concept of the distance in linear spaces. So why do we have to introduce the concept of distance in linear spaces? We have we are dealing with not only finite cases but also infinite series and infinite spaces. So to give some meaning to these infinite spaces, we discuss about their convergence and many other properties. And to discuss about these properties, we have to introduce the concept of distance. And the best way to introduce this concept in linear spaces is using the notion of norm. So the next slide is about norm spaces, or next thing we have to discuss is about norm spaces. But before going to the definition, we have to first understand what is meant by a norm. A norm is basically a function from the space E to the set of real numbers which satisfies the three following properties. First one is norm of x is greater than or equal to 0, and norm x equal to 0 if and only if x equal to 0. The second one is norm of lambda x is equal to lambda into norm x, and the third property is that norm of x plus y is less than or equal to norm x plus norm y. And here all these properties must be satisfied for every x and y belongs to E, and for the constants which are element of R, or it can be C also, since we have told in the previous section we are dealing with real numbers, or the field is real numbers or complex numbers. So this is the definition of norm. It is basically a function from the given linear space to the set of real numbers which satisfies the following three properties. Now, two things which we can notice. The first one is that the distance, we are introducing the concept of distance, so there must be a relation between distance and the norm that we have defined. So the distance d of xy between 2 points x and y is the norm of their differences. That is, d of xy will be equal to norm of x minus 1. Now, what is a norm space? Now we have a linear space and we have defined a function on it. The linear space along with this function or along with this norm gives us the norm spaces. And throughout this discussion or this chapter, we are going to denote the norm spaces using the letter capital X. Next, we are going to define the concept of stronger or weaker. So for that we have to consider two norms. The definition is as follows. The norm 1 is said to be stronger than norm 2 if we can find some constant c greater than 0 such that norm x2 is less than or equal to c into norm x1 for every x belongs to the linear space E. Now similarly, we can define the equivalence of two norms. Two norms are said to be equivalent if we can find two constants, one is capital C and the other is small c, such that both of them must be greater than 0, such that c small c into norm 1x is less than equal to norm 1x, which is further less than equal to capital C into norm 2x for every x belongs to E. So that is it for today's session. What I want you guys to do is to go through the examples which are given in page number 8 of the textbook, and you must verify whether these spaces are all norm spaces or not. So to check whether the given space is a norm space, we must check the three properties of the norm. We must check whether all these properties are satisfied. So thank you. Stay home, stay safe.